Question is, consider the network diagram given in the figure. Find out the value of V1. In order to find out the value of V1, apply the KCL at node A. That is V1 by 20 plus V1 minus 10 by 20 plus I1 equals to 0. Here V1 minus V2 equals to minus 1 volt. This is equation 1, this is equation 2. Here V2 equals to 10 I1, this is equation 3. Here is V1 minus 10 I1 minus 1, that is V1 equals to 10 I1 minus 1. So if we substitute equation 4 in equation 1 and solve for V1, then we will get V1 as 2 volts, which is option B is correct. In order to find out the VThevenians across the terminals XY, apply the KCL at node A, that is VThevenians 10 minus VThevenians divided by 20 equals to I1. Here indicated with 2. VThevenians minus V2 equals to minus 1 volt, V2 equals to 10 I1. So VThevenians equals to minus 1 plus 10 I1. So I1 equals to VThevenians plus 1 by 10. So from this equation, if we substitute this equation into this, that is 10 minus VThevenians divided by 20 equals to VThevenians plus 1 divided by 10, that is 2. 10 minus VThevenians equals to 2 VThevenians plus 2, that is 3 VThevenians equals to 8, that is VThevenians equals to 8 by 3 volts, which is option C is correct. Consider the solar cell characteristics given in the figure, which are calculated at temperature equals to 300 degrees Kelvin and the reverse saturation current equals to 1 nanoamp. Calculate the open circuit voltage. Here open circuit voltage for a solar cell is given as Vt, which is the thermal voltage, into load current divided by the reverse saturation current plus 1. We know from the characteristic IL equals to 100 milliamp, that is this one is the IL. IS is 1 nanoamp. If we substitute this one, we will get open circuit voltage as 0.48 volts. Question is, consider the solar cell characteristics given in the figure. Calculate the output power at a voltage of 0.35 volts. For a solar cell, the power output is given as I into V, whereas I equals to IL minus IS e power V by Vt minus 1 V. Here IL is Here IL is 100 milliamps, that is 0.1 into 0.35 minus and 10 power minus 9 into 0.35 e power 0.35. The thermal voltage at a temperature of 300 Kelvin is 0.026 minus 1. If we evaluate this equation, we will get answer as 34.77 milliwatt, which is option A is correct.
A circuit breaker is employed in a generator rated at 20 MVA, 33 kilovolts and XD dash, that is transient reactance value is 25% and generated EMF is Eg is equal to 1 per unit. Okay, then what we have to find in this question is transient symmetrical RMS current. He has given a multiplication factor of 1 by 1.2. Okay, that we can use later. Okay, now let us find transient symmetrical RMS current. What is transient symmetrical RMS current? Okay, I dash is equal to Eg by XD dash. Okay, I dash is equal to Eg by X dash, where Eg value is 1.0 by XD dash. Transient reactance is 25%. So this is 0.25 J. Okay, now this is equal to 4 at an angle minus 90 degrees per unit. Okay, option B is correct. Next question in this one is interrupting current of a 3-cycle breaker in kiloamperes is. Okay, we have to find interrupting current of a 3-cycle breaker. Okay, interrupting current in per unit. Okay, interrupting current in per unit is equal to multiplication factor times of 4 at an angle minus 90 degrees. Okay, so this is 4.8 at an angle minus 90 degrees. Okay, now what is base current here? Base current is equal to 20 MVA. Since 20 MVA, okay, 20 into 10 power 3, okay, by, you can also take as 10 power 6 MVA by 33 kilovolts. 33 into 10 power 3, since it is 3 phase, multiply with root 3. Okay, base current you will get it as 350 amperes. Okay, now what is interrupting current here? In kiloamperes we have to find. We know the per unit value is 4.8 at an angle 90. Okay, now what is interrupting current? In question he asked in kiloamperes. So convert per unit into amperes. So 4.8 into 350 amperes. So this is 1.68 kiloamperes. Option C is correct answer.
Question is, consider the system shown in the figure is. Here x of t is the frequency domain sequence and thus h of f performs the filtering action on x of k, and this block corresponding to a low pass filter whose time constant equals to 1. Here x of k we can write as follows. X of k equals to 4 delta of n delta of k plus 3 delta of k minus 1 plus 3 delta of k plus 1. If we apply the time domain equation, that is x of t, then we will get 4 plus 6 cos 2 pi t, which is a continuous equation. Even though x of k is discrete domain signal, x of t is the continuous time signal. If we apply this x of t to the h of s, which performs the filtering action on the x of t, see, the frequencies present in the x of t are the DC signal as well as the frequency is 1 Hz. Here for this term frequency is 0 Hz. For this term the frequency is 1 Hz. Hence g of t equals to 8 plus 6 cos 2 pi t. Hence option A is correct. Question is, consider the system shown in the figure. Find the DC component signal y of t is. Means we have to find out the DC component present in the signal y of t. Here g of t is given as 8 plus 6 cos of 2 pi t. We are applying the g of t to the low pass filter whose time constant equals to 1 second, that is RC equals to 1 second. The transfer function of the low pass filter is 1 by s, 1 plus 1 by s, that is 1 by s plus 1, that is equals to h of s. H of omega equals to 1 by 1 plus j1 j omega. Here the g of t equals to 8 plus 6 cos of 2 pi t. Here omega equals to 0 as well as 2 pi. These are the frequency components present in the g of t. Here h of 0 equals to 1, h of 2 pi, that is omega equals to 2 pi f, f is 1 hertz, so 1 by 1 plus j2 pi. So y of t is equals to 8 h of 0 plus 1 by under root 1 plus 4 pi square 6 cos of 2 pi t. Here the DC component present in the y of t is 8, which is option D is correct.